Welcome, calculus students, to the final video notes lesson for this entire school year. That's right, this is the last video you will have to watch in calculus this year. Woohoo! So excited. So what we're going to look at in this video are some AP style FRQ questions having to do with a specific application of integration, which would be area and volume style problems. So what we've been working on lately in chapter 6, basically. Now, if you look at this first one here, what we're given are the graphs of two equations. We've got y equals tan x, which is this one here. That's kind of going through the origin here. And then we have the equation y equals 2 minus x to the third, which is a cubic function with a y-intercept of 2. So it's going through our y-axis right here, and it's curving down this way. So that's our 2 minus x cubed function. And we have two different regions that are being created. So we've got the region R, which is bounded by the x-axis here, the curve y equals tan x, and the curve y equals 2 minus x cubed. So kind of this little triangular region there. And then we have our region S, bounded by the y-axis over here, and then those same curves, the 2 minus x cubed and the y equals tan x. So it's this region kind of in the upper left corner. Now part A is asking us to find the area of R. And again, R was this sort of triangular region down here bounded by the x-axis and the two curves. So when we're finding the area of a region, what we typically want to do is split the area up into many different rectangles, where the height is determined by the higher function minus the lower function, and then the base is just like a dx type of thing. But I'm noticing the way that these graphs intersect right here, that if I was to find this area with respect to x, I would actually have to split this integral into two different parts based on whatever this x-coordinate of this point of intersection is right here. And I'd have to use the tan x curve if I wanted to go from 0 to that x-coordinate of integration. And then I would just be finding the area bounded by tan x and the x-axis. So just an integral of tangent basically from 0 to x. And then I'd have to do another integral, which goes over to this point here, which would be my x-intercept of the 2 minus x cubed graph. And then I would again be finding the area bounded, or the area below that curve, but above the x-axis. So basically just an integral of 2 minus x cubed from this point of intersection to the x-intercept. So I'm kind of thinking that instead of integrating with respect to x for this one, I think instead I'm going to integrate with respect to y. So when you're finding the area of a region with respect to y, you do something similar where you split it into rectangles, but this time the rectangles are being laid down horizontally. So the height, if you will, is sort of this horizontal length, which would be the difference in these two x coordinates, which would so I'd have to get these expressions, I'd have to solve them for x and get them in terms of y. So I could figure out a way to get that x coordinate and that x coordinate as a function of y. And then I would subtract the two to determine this horizontal length. And then the height of each rectangle would be all of these different dy values, all these change in y's as you go from bottom to top. And that's another thing, when you integrate with respect to y, you stack these rectangles vertically, so they're kind of being stacked along here. And so you would go from 0 to the y coordinate of this point of intersection here between the two curves. But the nice thing about it is I would only have to use one integral as opposed to two. So again, what I'm going to do is I'm going to set up my integral. It's going to go from 0 because it is bounded below by the x-axis, so that's where y equals 0. And it's going to go up to this y-coordinate of the point of intersection, which we're going to find in a moment. What I am going to have to do, though, is I'm going to have to get each of these curves to be in terms of y. So maybe I'll start with the cubic function. So right now I have y equals 2 minus x cubed. And what that's doing, this equation, y equals 2x cubed, is it's giving me a y value. It's telling me, like, for any x, so I could pick any x along the x-axis. If I plug in that x, it'll tell me how tall the y value is. So it's giving me kind of a vertical length. But when I want to switch that around and be able to, given any y value, figure out how far to the right I have to go, right? So when I want to find a horizontal length, what I want to do is isolate that x and get it in terms of y. So I'm going to start by subtracting the 2, removing the negative, and cube rooting. So I can see that these x coordinates, so these x distances from the y-axis to the right out to this curve, can be found by taking any y value, plugging it into the cube root of 2 minus y, and that'll give me my x value. So that would be my greater x value, right? Because the cubic function, if you're looking at it in terms of a horizontal distance from the y-axis, is further away than the tangent function is. So that would be my greater function. So I'm going to start by taking that function, the cube root of 2 minus y. That would be considered my greater function. And then, because I don't want to use this whole entire length, right? I want just the length between the two curves, right? I want just these lengths. So what I'm going to have to do is subtract the part that goes from the y-axis to this equation y equals tan x. I need to subtract all those away so that all I'm left with is just the distance between the two curves. So these are each x coordinates on the graph of y equals tan x. So similarly, I will have to get that as, I'm going to have to solve that for x and get it in terms of y. So for that, I'm just going to use arctangent. So if y is equal to the tangent value of x, then x would be the inverse tangent or the arctan value of y. So what this is giving me are these horizontal distances from the y-axis out to the curve y equals tan x, because they're giving me the x coordinates for each of the different y values. So if I take these values, which we're going from the y-axis out to the further function, out to the 2 minus x cubed graph, if I take all those, and then from that, if I subtract these distances going from the y-axis to the tan x curve, so if I take all those out, then what I'm left with are just these distances here between the two curves, these horizontal distance between the two curves. So that would be the height of each of my rectangles. So let me write that here. So each of these are the heights, so to speak. Of course, they're laying down sideways, but they would be considered the height of the rectangle. And then if I multiply that by dy, which is like this sort of vertical change between each height, so it's considered the base of each rectangle. So the heights times the base, and I do that for all the y values starting from 0 all the way up to this y coordinate. That's the y coordinate of this point of intersection, which we're going to find in a moment. If I sum all that up, and we're imagining infinitely many, then what I'm doing is I'm basically finding the area of that region. So what we're going to have to do now, of course, is find this point of intersection. So this point of intersection, as you're about to see, is not going to be like nice, easy whole numbers. In fact, they're both the x and the y coordinates are going to be long decimal values. So what we're going to do is we're going to find and store both of those coordinates of our point of intersection here between y equals tan x and y equals 2 minus x cubed using our calculators. Okay, so what I've done here is I've entered in these two equations for my curves in my y equals menu for the graphing calculator. Now you want to make sure, because this is a trig function, so you just want to always make sure you're in radian mode when working with trig functions in calculus. Okay, but let me go back to my y equals. I have my equations here. Now if you notice when I click graph right away, it gives me a window. It gives you like a standard viewing window from -10 to 10 for both the x and y axis. But you can see from this graph here, I'm just kind of want to see this part of it. So I don't need this full window. So I'm going to kind of close in here on my x and y axis. I'm going to go from the x value of -1, which would be probably right around here, out to maybe an x value of 4 or 5. And then I'll kind of do something similar for the y value. Maybe I'll go up to 5 for that one. And then you can see it'll kind of give us a picture that looks a little bit more like what we see on our test page. Now what I want is to find is this point of intersection right here. So to do that on your calculator, you're going to hit the second button and then the trace button, which opens up this calc menu. Okay, so then you would hit 5 because we're looking for a point of intersection. Now when you do that, you'll be given this prompt, first curve, ? And it'll give you the equation of your curve. And it looks like my point that I'm on right now is 1.514. So I kind of want to go backward a little bit. I want to get closer to the point of intersection. There we go. So I can see I'm on the first curve, so I hit, yep, that's the one. And then it'll drop that point down to the second curve and give you the equation. You can say, yep, that's the one. And then it says guess, and you can maybe scroll closer to where you can see the point of intersection to be between the two. Hit enter, and it will calculate that point of intersection for you. And as you can see, both the x and the y coordinate are these long decimals. So I want to store both of these so I can integrate with either respect to x or y without having to round these decimals, because every time you round, you lose accuracy. It also saves me time. This way I don't have to keep writing these down on my paper either, or retyping them into my calculator. So right after you calculate these values, what you want to do is go straight back to the main menu. So you hit second mode, which basically means quit. It'll take you back here. So because I want to store both x and y, what I'm going to do this time is I'm going to hit this variable button. This is what the calculator understands the x variable to be. So it understands this is the x coordinate that we're saving. And then I'm going to hit the stow button to store it. And then I'm going to just, for this case, I'm going to store it as alpha A. I can pick any one of these alphas that I want to, but for this one I'll choose alpha A and enter. And there you can see that x coordinate is with a few extra decimals in there, because the calculator is able to store the unrounded decimal value. Now to store the y coordinate, what you'll have to do is hit alpha y. That pulls up the y coordinate of that ordered pair, and I'm going to store that, but I need to store it as something else, right? I don't want to use A because I'm already storing this value there. So maybe I'll just use B right next to it. And then there is my y coordinate of my point of intersection, and now they are both stored in my calculator for future use. So after finding your points of intersection, what you should do is you should define them on your paper. So there should be somewhere very clear and easy to find where you have stated that your point of intersection is going to be defined as A and B, or whatever you're choosing to define them as. And then you will have to write out what you found each decimal to be. But this is the only time you will have to write it. Then once you have these decimals written down, you can then just refer to them as either A or B, whichever one you're using in your answer on your paper. So here is my integral up here that I'm going to use to find the area of region R. And I'm going to go from 0 to B, right, to the y coordinate of the point of intersection. So I'm going to write B up here as my upper limit of integration. Now at this point, I can evaluate this integral on my calculator. If the question is part of the calculator OK part of the exam, then you can do all the evaluating of the integrals with a calculator. Okay, so now that we have everything we need here, we can go ahead and just do the Math 9 to be able to evaluate our integral. So I can see that I want to go from 0 to the value of B that I stored. So I'm going to hit alpha B, and it's using this decimal for that. Now I know on my paper I have it written as this cube root of 2 minus y, and then arctan of y, and then dy. But on the calculator, we're going to have to kind of put all that in terms of x. I'm still going to use these functions, the cube root and arctan, but I'm going to use x as my variable instead of y, because that's the only way that the calculator can do it. So for the cube root, I'm going to go to the math menu and option 4, and then I'm going to type in 2 minus the variable key. So the variable key is always just automatically in terms of x. And then I'm going to subtract from that the inverse tangent. So to access inverse tangent, you'd have to hit second tangent, and then that'll pull up the inverse tangent, which is the same as arctan. And then I hit the variable button, which is always in terms of x, even though we understand that this is really the function in terms of y. And then we'll hit x here. And then maybe just one little quick run through, make sure we got all that right. We got our limits in there. And so then we can hit enter and make sure again that you're in radian mode. Now remember also with the AP test, your answer has to be correct up to 3 decimal places. So you can either round or truncate. Truncate means you just cut it off at the 3rd place. I would just ignore all these other decimals. Round means you would round it either up or down, or you would either leave it or round it up based on this 4th decimal place. Although in this situation, even rounding gives me just 0.729. So I can write my final answer on my paper. I've got my limits here, my integral written out, and then my final value for it, which was 0.729 rounded and truncated. Now part B of this question is asking us to find the area of the other region, S, the one bounded by the y-axis and the two curves. So I'm noticing with this particular region that I could easily integrate this with respect to x, because if I use vertical distances for the heights of my rectangles, there is a clear function that is always greater than the other function. In other words, it doesn't split at some point between here and here. So I do still need this point of intersection, which we found the values of earlier, but I can integrate from 0 to a, to the x coordinate of that point of intersection. And this curve, the y equals 2 minus x to the third, is always greater than or above the second curve, which was y equals 10x. So I can integrate with respect to x and still only have one integral. So that's what I'm going to do for part B. So I write my integral out here, and again, I can go ahead and just call this upper limit of integration a, assuming that I have defined it already when I was doing part A in my problem. So I can just use that here as well. Now remember, the 2 minus x cubed minus 10x, this expression is representing the height of a rectangle. So it's as if I took this area and split it into rectangles, and it's these vertical distances here, which are taking the y coordinates from the cubic function, subtracting from them the y coordinates from the tangent function, giving only the distance, the vertical distance in between the two. And then the dx is representing the base, the thickness between each of these rectangles along the x-axis from 0 up until a, which was this point of intersection right here. So I can also just plug this into my calculator and round my final answer, or truncate it, to 3 decimal places. Okay, so for this integral, I want to show you something else with the calculator, because if you remember earlier, we had entered in tan x for our y1 and 2 minus x cubed for our y2. So one thing you can do when using Math 9 on your calculator is I'm going to go from 0 to the x coordinate of the point of intersection, so 0 to alpha a, and then I can just go to alpha trace and pull up whichever function I want that's in my y equals menu. So tangent was my y2, so I'm going to pull that one up. Or sorry, not tangent. The 2 minus x cubed was my y2, so that one came first. And then tangent was my y1, so I'm subtracting tangent, and then dx. Now, these equations were not very complicated, so it would not be hard to just type them in here. But this is just handy in a situation where your equations maybe are more complicated and you don't want to have to keep retyping them in. But anyway, you can just call up both of those functions here and then hit enter, and it'll give you your answer for your area here. Now in this case, you could either write 1.160, that's if you're truncating, so you're just cutting it off after the third place, or you could round this up to 1 based on the 4th decimal place of 5. So that's what I'm going to do here. I'm going to put the rounded answer to 3 decimal places. So there is my final answer for part B. So now we come to part C, where it wants us to take this region S and revolve it around the x-axis. So that makes this a volume of solid of revolution problem. And whenever you are confronted with one of those, the first thing you would want to check is to see whether or not you're going to need to use the disk method or the washer method. So what you look for is whether or not the axis of revolution, which in this case is the x-axis, whether or not that is one of the boundaries of your region. Now remember, our region S was bounded by the y-axis, the curve 2 minus x cubed, and the curve 10x. So this is our region S. We're revolving it around the x-axis, which is not a boundary of one of the regions. In fact, there is a gap between the lower boundary to our region and the axis of revolution. So that gap is what causes us to realize that we're going to need to use the washer method. So we're taking this region S and revolving it around the x-axis, which is a type of vertical revolving, and would kind of reflect this part of the curve down here-ish and create these cross sections that look like washers. They would have these circular gaps in the middle there. So the solid itself would kind of maybe look a little bit like a bundt cake with this sort of cone-shaped gap in the middle and then these rounded edges. So when you're using the washer method, you've got a longer radius, which I'll use capital R to represent, and then a shorter radius, which I'll use lowercase r to represent. The longer radius is the one that goes all the way from the farther edge, the farther boundary of the region, all the way down to the axis of revolution. It's that curve, that distance between the two. So in this case, the farther, when I say farther, I mean farther away from the axis of revolution, which is the x-axis. So it's the one further above the x-axis, which is the y equals 2 minus x cubed, this one here. So that height, that vertical height, is the length of my longer radius, the one that goes all the way from the edge of the solid to the middle of the solid. Now the little radius is the distance from the boundary of the region that's closer to the axis of revolution. So it's kind of like the radius of the gap. When we revolve the region around, there's sort of this circular gap in there, and the little radius is sort of the radius of that gap. But it's always the distance from the boundary of the region that's closer to the axis of revolution. So in this case, it's the y equals 10x graph. That vertical height, the distance from the graph y equals 10x to the axis of revolution, which is the x-axis, is our shorter radius. Okay, so now I have my two radii. So I know that the area of my washers is going to equal pi times the large radius squared minus pi times the small radius squared, which in this case is pi times 2 minus x cubed squared minus pi times tan of x squared. So what this is finding is the area of the big circles, the one that stretch all the way from the outer edges to the middle. And then we're subtracting from that the small circles, which are these little circles in here, so that we basically end up with washers, circles with holes in the middle. But they each have a common constant, so you can pull out the pi and just be left with each of the radii squared. So here is the area of my washer. Now, if I want to get the volume of the full solid, what I do is I integrate. I sum up infinitely many areas. So I'm going to integrate again from 0 to this point of intersection. So let me get some of this stuff written off here. So I'm going to integrate from 0 to A, which was the x-coordinate of that point of intersection we had found earlier. And I'm integrating all these areas of all these washers. So I'm kind of summing up infinitely many washer areas. I'm going to go ahead and put this constant pi on the outside because we know that rule of integration, which says you can pull constants out. So I just need to plug this integral into my calculator and get its value. So to do that, I'm going to start with math 9. And I'm going to integrate from 0 to A. So we've stored that in our calculator so I can continue to use that over and over. And I'm going to square the 2 minus x to the third function. So if you remember, I had stored that in my calculator as y2, and the 10x was stored as y1. So in my integral, I'm going to go to alpha trace, and I'm going to go to y2, because that was my 2 minus x cubed function, and I'm going to square that. Then I'm going to subtract, and I'm going to do alpha trace, and then go to my y1 function. That was my tangent function. And then I'm going to square that and then integrate this with respect to x. Now notice I don't have the pi in here because what I'm doing right now is I'm getting, this would be the decimal answer that I need to multiply to pi to have my full volume. So we don't want to forget about the pi out here. But sometimes it's nice to write your answer and then just say 2.652 pi. So I'm going to keep this decimal here so that I see it, but then I'm also going to take it and multiply it to pi so I can have that answer as well. So you can either write your answer as 8.331 or you can write it as 8.332, it's one or the other, or you could write it as 2.652 times pi. So on my paper, I write my final answer and we are done with this problem. Let's take a look at the scoring guidelines. So a typical FRQ problem on the AP test is worth 9 points. So we can see that for this one, they split each part into 3 points. And it looks like the points were split up pretty similarly between all 3 parts. They were giving out 1 point for the limits, 1 point for the integrand and 1 point for the answer. The only difference is in part C where they added this constant, limits n constant to that first point. I'll kind of explain what that means in a second. The limits in general are talking about our limits of integration, like from what limit to what limit are we integrating. Now notice for part A, they actually had 3 different options that you could have used. We used this second option here, the one that was with respect to y. So if they were grading our problem, they would look to make sure that we integrated from 0 to b. If you recall, b was the y coordinate of the point of intersection between the two curves. So as long as you define that somewhere on your paper, then you can just call it b later on. So they'd be looking to make sure it was going from 0 to b as opposed to 0 to a. And then they would, that's our limits. So that's what that 1 point is, the 0 to b. The integrand is referring to whatever we write inside the integral for all of these. So again, for number 1, they would be making sure that we had the right functions, that we would have used the equations in terms of y, so the 2 minus y, the cube root of 2 minus y, and then the arctangent or tan inverse of y, dy, so they'd be looking for a dy here instead of a dx. So that part would be worth 1 point, the correct integrand. And then of course the correct answer is the number part, but you only get that point if you have it correctly rounded to the 3rd decimal place. So these numbers would have to match exactly, 0.729. You can always go more than 3, but you can never go less than 3. The first 3 decimal places have to be exact to get that 3rd point. And just a really quick side note for part A, I just wanted to show you the other way you could have done that question if you wanted to do it in terms of x. We had talked about it briefly at the start of the problem, but just to show you again here, basically you would integrate tangent separately. That was like the first side of the region, and you'd have to go from 0 to a, the x coordinate of this point of intersection. And then you could, that was the integral of tangent, and then you could take the integral of 2 minus x cubed, that was sort of the right side, from that point A to the x-intercept of the 2 minus x cubed graph, which was cube root of 2. So you could go from A to that number of 2 minus x cubed, and then just add those two areas together, and that also would get you to the 0.729 that this integral does. So just another option for part A. And then in part B, same spread of points. So we did this according to their first option here, but they would be checking to make sure your limits were 0 to a, that's 1 point. Your integrand is the cubic minus tangent dx, that's the 2nd point. And then you can put either one of these decimals, but that's it, either one of these decimals to get that 3rd point. Now for part C, they added this constant. The constant is pi, because we were using the washer method for part C, and so our cross sections are basically circles, right? They're washers. So it's pi times this radius squared minus that radius squared. So they would be looking to see that you had that pi as part of your integral. And then of course our limits from 0 to a, and then the integrand here, which were these 2 functions cubed and then being subtracted, and then dx. And then of course that answer, it could be written in one of these 3 ways. So let's move on to question 2. This is another one that will allow the use of the calculator, so we will take advantage of all those helpful tools again. So here we have the region R enclosed by this polynomial function and then the horizontal line y equals 4. That'd be this one right here. And the first thing it wants us to do in part A is, again, find the volume of a solid of revolution. When I take this region here and revolve it around the horizontal line y equals -2, which would be down here. Maybe I'll just dot this line. So again, whenever you are about to start a volume of solid of revolution question, you need to check with yourself whether or not we're going to use the disk or the washer method. So again, because this axis of revolution down here was nowhere near either boundary for the region, there's basically a huge gap between the boundary of the region and the axis of revolution. This is definitely going to be a washer method. So again, we're revolving this around this horizontal axis, which is a kind of vertical revolving. It's an up-down revolving. So this upper part here is going to revolve and be reflected down here. Forgive my drawing skills here. And our cross sections are going to be these giant washers that go all the way from the outer edge of the region to the axis of revolution. And you're going to see they have this large gap in the middle as well. In fact, the gap gets quite large as you move to the outer edges of the region. So what we're going to have to do is find an expression for our larger radius. Again, the larger radius is the one that goes from the boundary of the region that's furthest away from the axis of revolution. So it goes all the way from the outer edge to that axis of revolution. And so how we typically find the expression for that is we subtract the two. We subtract the further region away from the axis of revolution, which in this case would be 4 minus -2, which actually gives us 6. You can see that this distance from the from the x-axis to the line y equals 4 would be 4. And essentially we're adding this distance from the x-axis to the line y equals -2, which is 2. We're basically adding that up to say that my longer radius is going to be 6. So in this particular situation, because the outer boundary of my region was linear, or horizontal I should say, then the radius between it and my axis of revolution is constant. So this solid would have kind of like it would look like a cylinder on the outside with a sort of hourglass gap in the middle of it. So that's kind of what the shape of this would look like. So my outer radius, or my longer radius, is actually the one that's constant. Now the shorter radius is the one that goes from the part of the region, or the boundary of the region, that's closer or closest to the axis of revolution. It would be the distance between those two things. So it would be the distance between this curve, which is y equals x to the 4th minus 2 minus x cubed plus 4, and the axis of revolution, which is where y equals -2. So to find the distance between those two things, we simply subtract them. And so I can go ahead and combine my like terms here. And I get this as my expression for the shorter radius, because that's the one that's sort of changing as you change x values along the x-axis. Are these distances going from this lower boundary of the region to the axis of revolution. So for our integral setup, we're going to go from 0 to this point of intersection right here, which we're going to have to find. I'm going to call it A again. Once I find it, I'll solve it as, or I'll save it as A. And then it's going to be pi times the big radius squared, which is 6, minus pi times the little radius squared, which was this expression here. And then this will all be in terms of dx. Now, because each of these has the pi in common, you can go ahead and just pull it outside of your integral. And we could even just plug it in like this. So we're going to integrate this in our calculators and round our answer to 3 decimal places. So again, I've started by typing in my 2 boundaries for my region into my calculator here. So I can go ahead and graph them. Now again, you can see that the window is a little bit more zoomed out than the one on our paper. So we're going to want to zoom in on our view as well. I'm going to try -1 to 5 for both to see if that gives me a better view. Yeah, that looks a lot better. And what we're trying to find is this point of intersection right here. So I'm going to do second, calc, 5. I'm going to go ahead and get close to my point of intersection. So again, it's saying first curve, enter, second curve, enter, guess, enter. So you really can just sort of hit enter 3 times as long as you've like toggled over to the point of intersection. Now this one I don't really need to store because it's just 2.3. So if it's a terminating decimal, then you can just use it, you know, you can just type in 2.3. So I'm going to kind of keep that in mind, that that's my x coordinate of the point of intersection. So what I'm going to do is type in my integral, so math 9. I'm going to go from 0 to 2.3 because that was my x coordinate of the point of intersection. Then I'm going to do 36, that was my 6 squared, minus, and then I have these parentheses, x to the 4th, minus 2.3 x cubed, plus 6. That was our radius expression. And then I'm going to square that. I had to put that in parentheses and square it. And then put in x here. So we're integrating with respect to x. Now remember, I haven't multiplied in the pi yet, so keep that in mind. This is going to have to be multiplied to pi. So you could either say, okay, the volume is 31.471 times pi, or you can go ahead and just multiply it to pi. and then get 98.867 or 98.868. So on my paper here, I'm going to take off this A because I ended up finding a decimal that I didn't need to store. So I'm just going to go ahead and call this 2.3. And then I integrated that and got 98.868 as my answer, rounded or truncated to the third decimal place. Now for part B, they're asking us to do a volume by cross-section perpendicular to the x-axis. That means we're going to integrate with respect to x. And region R is the base. So this here is the base of our solid, and we're going to be stacking isosceles right triangles on top of this solid. Now remember, an isosceles right triangle is a right triangle with two equal sides. So here it's saying that the leg is in the region. So what that means is that this leg is equal to the height, and then they'd be kind of stacked this way. So imagine a bunch of these right triangles just stacked right on top of this region where the leg is equal to the height of this isosceles right triangle. So the area, so what we have to do first of all to find volume by cross-section is we integrate from, in this case we're going to again go from 0 to 2.3. So we now know that this point of intersection over here is 2.3 comma 4. So we know that they intersect at the x value of 2.3. So I know I'm going to integrate from 0 to 2.3. This is with respect to x since the cross sections are perpendicular to the x-axis. And it's the area of the cross-section times dx, which is the little changes in x as you go along the x-axis here. So since this is the area of an isosceles triangle, it's going to be 1/2 base times height. Now these are equal to each other because it's isosceles, and the base or the leg of the triangle is in the region. So what we need to do is figure out the distance from the line y equals 4 down to the curve y equals x to the 4th minus 2 minus x cubed plus 4. So to do that, we just subtract the two things. So the leg of the triangle will be 4 minus that equation. And then if I distribute the negative and combine like terms a little bit, that would end up equaling just negative x to the 4th plus 2.3x cubed, because the 4's would cancel out. So this is going to give me the leg of the triangle, but the leg is equal to the height of the triangle. So to get the equation for my area of the triangle, I'm going to do 1/2 this times itself, or 1/2 negative x to the 4th plus 2.3x cubed squared. Leg times height, but they're equal to each other. And I'm integrating that from 0 to 2.3. I'll go ahead and pull the 1/2 out in front and just have this expression in my integral squared. And then I'll integrate that with respect to x. This question was also on the calculator part, so we can go ahead and evaluate this on our calculators. Okay, so on our calculators, we're going to go ahead, to get the integral, we're going to do math 9. And then I'm going to integrate again from 0 to 2.3. And then I'll type in my equation here. So I need to put parentheses. I have negative x to the 4th plus 2.3x cubed. And then I'm going to close that parenthesis and square it. And all of that is inside my integral, which is what that other parenthesis is for. And then type in my dx. Now remember, I forgot to type in the 1/2 here. So you can either do that first, or you'd have to be careful and remember to do it at the end. So I need half of this, right? So I can either multiply by 0.5 or divide by 2. But this would be my volume here. Rounded to the third decimal place would be 3.574. And there is my volume for part B. Now part C was kind of a unique style problem. So here it's talking about some vertical line x equals k, which is not shown in the picture. That's going to take this region R and divide it into two equal areas. So it wants us to just write an equation that has integral expressions in it that if we solve that equation would give us the value of k. So I'm going to draw in a vertical line here that roughly cuts the area of this region into two equal parts, this part and that part. And here's our point of intersection here, which would be when x is k and y is 4. So what I could do, or what I know, I should say, what I know is that the integral from 0 to k of the distance between y equals 4 and the equation for the polynomial, so I'm going to subtract those two again. So again, that distance there can be found by doing 4 minus that equation for the polynomial. Now we had done this, we had figured this out earlier, that it's actually negative x to the fourth plus 2.3x cubed plus 0 because the 4's cancel out. So this represents that distance between the two curves. So if I wanted to find this area from here to k, I could just integrate from 0 to k of that distance dx. That would give me this area here. But according to the wording here, the regions have equal areas. So the other area would be from k to 2.3, so from here to that x coordinate of the point of intersection, and it would be the same equation. It would be from 4 minus the polynomial, which equals this. So what I know is that these expressions are equal to each other. So if I set them equal to each other, what I have here is an equation, right? This setting them equal to each other forms an equation. In each side of the equal sign, I have an integral expression, both containing the variable k. And by using anti-differentiation methods, I could technically solve out each of these integrals, and I'd have a k in my expression, which would create an equation with k in it that I could solve to find k. Of course, it told us not to, thank God, but I could. So this is my answer. This is my equation with my integral expressions in it that could be used to solve for k. And that concludes question number 2. So in question 3, we come to a question that does not allow the use of a calculator. So when we are evaluating our integrals, we'll have to do that work by hand for this one. So the first part is asking us to find the area of this region R here that is bounded by these two curves, whose equations are given up here. The f of x equals 2x squared minus 6x plus 4, and then the g of x, which equals 4 times cosine of pi over 4x. Now it doesn't tell us which curve is which, so it does require us to have an understanding of these types of curves to know which one would be which. So what I'm hoping you notice about f of x is that the highest power of x is 2, which makes this one a quadratic, and the graph of a quadratic equation always looks like a parabola. So that equation is referring to this curve here. This one, that kind of goes down, and then it would go up again on the right if I was looking at the whole graph. So that is the graph of a parabola, and therefore this curve belongs with the equation for f of x. Then the cosine graph, as you know, the parent function starts at its max value, and then it goes down to the min, and then back up to the max, and then kind of keeps oscillating like that. So we know that it begins at its maximum value, which for the parent function is 1. For this one here, since it has the a value of 4, it would start at a max of 4. And then if I were to let the graph continue, it would go down to a minimum of 4, negative 4, and then it would continue to go up and then down and oscillate. But again, we're just kind of looking at just this part of the cosine graph. So this top curve refers to the equation for g of x. So we're trying to find the area of this region R. So the process for that is we integrate and we subtract the greater function minus the lesser function. And what that does is it's telling us what the height of each of these different rectangles would be, because that's kind of how we understand this. We kind of cut this area into rectangles, and they each have their little bases here. Of course, if you add infinitely many of them, so the base is represented by dx. So we kind of imagine you stick more and more rectangles in here, and what that does is it makes the dx, the base of each rectangle, get smaller and smaller until you have basically infinitely many of them. And so that's what gives us this entire area of this region. So these vertical lengths that are representing the heights are the distances between these two equations. So it's this y value minus this y value. So if I take the y value of the taller function and then subtract away from it the y value of the shorter function, all you have left is that vertical distance between the two functions. So that's why you take your higher curve, which in this case is the cosine, and subtract from it the lesser curve. And then we have to figure out what our points of intersection are, because that'll help us determine the lower limit and upper limits of integration. So for this one, we can fortunately see those points of intersection right from the graph. So they go from 0, 4 to 2, 0. And we're integrating this with respect to x because these heights are vertical. And so it's going to go from 0 to 2, from those x coordinates of the point of intersection, from the first one to the last one. And the cosine function is the greater function, so that's going to go first in my integral. And then I will subtract from it the quadratic function. Then I'm going to go ahead and split this integral out so I can integrate the cosine part separately, because I can see I'm going to need a u substitution for that. And then I can integrate this polynomial part separately. So I think I'll do the polynomial part first because that's a little easier, and then I'll come back and do my u substitution for the cosine part. So I'll take the antiderivative for each of these terms, and then I have to evaluate them from 0 to 2. I'll simplify a little bit. Then I'll evaluate at each endpoint. Of course, when I plug in 0 to each of these terms, they each have an x, so then the result would just be 0. So I'm just left having to add these three terms together. So I end up with -1 and 1/3, or we can think of that as -4/3, either way. So this number is the value for this part of the integral. So we know that this part of the integral equals -4/3, and once I'm done evaluating this part, I will add it to the -4/3. Okay, so the first thing I notice is that the thing inside of cosine is not just plain x. It's pi over 4 times x. And so that's the thing that I want to equal u, so that I can eventually just have the integral of cosine u. So I'm going to let u equal pi over 4 times x. But now when I change this to be cosine of u, I'm going to have to change dx to be some expression with du. So I have to figure out what du is. So if u is pi over 4 times x, then du will be pi over 4 times dx. And then that means that 4 over pi times du will equal dx, because I'd have to multiply by the reciprocal of pi over 4 to cancel it on the right side and move it to the left side. So when I remove dx from my integral, I'm going to have to replace it with 4 over pi times du. Also, when I'm doing my new integral, I'm going to replace these limits of integration with u values. So I can see that when x is 0, u would be pi over 4 times 0, which is still 0, so this will still be 0. And when x is 2, u will be pi over 4 times 2, which becomes pi over 2. So my upper limit of integration becomes pi over 2. The 4 is still there, but now inside cosine, I'm going to replace pi over 4x with u. And instead of dx, I'm going to replace that with 4 over pi times du. So then I can multiply these constants together, the 4 times the 4 over pi, and get 16 over pi, and pull that out of the integral there. And then I'm just left with the integral of cosine u du. So the antiderivative of that would just be sine u. So it's 16 over pi times sine u, and I'm going to evaluate that from 0 to pi over 2, which would be 16 over pi times sine of pi over 2, minus 16 over pi times sine of 0. Well, I know that sine over 0 is 0, so then that makes this whole second term go to 0. And sine of pi over 2 is 1, so 16 over pi times 1 is just 16 over pi. So that's the value of this first integral, basically this part right here. The value of that is equal to 16 over pi. So coming back to my area integral, right, which was the integral of the cosine function minus the quadratic function, it ends up equaling 16 over pi minus 4 over 3. That would be our value for the area of this, the area bounded by these curves, the area of this region here. So now in part B, it wants us to find the volume of a solid of revolution that's generated by revolving the same region R over the horizontal line y equals 4. So because this is a volume of solid of revolution problem, the first thing we should do is check whether or not we are going to be using disk or washer method. Now you may notice that there is a gap between the axis of revolution and the closer boundary to the region. So that indicates to us that we're going to need to use the washer method. The other thing you want to decide is whether or not you're going to integrate with respect to x or y. Now, because this rotation was around this horizontal line, it's kind of a vertical rotation. It's going to take this region and kind of flip it up this way. And your cross sections would look something like this. So it'd be these large circular shapes with these circular gaps in the middle. So the outer edge of it would kind of look like a bowl shape, sort of. And then the inner part would be sort of this cone-shaped gap. So in either case, though, the radius of each circle is standing vertically. It's a y value, and y is in terms of x. So we are going to be integrating this with respect to x because the radiuses are perpendicular to the x-axis. So what I need to do now is figure out my equation for the large radius versus the equation for the smaller radius. So to find the equation for the big radius, we look at the longer distance from the axis of revolution to the further boundary of the region. So this region is bounded by two curves, this quadratic one here and the cosine one here. Now, the axis of revolution was this equation y equals 4, which is further away from the quadratic expression, the 2x squared minus 6x plus 4. So that vertical distance will be the longer radius. And if you look at your cross section, the washer, the edge of the washer would go all the way down to that quadratic expression. So the radius would be the larger y value, which is y equals 4, minus the smaller y value, which would be these here, the 2x squared minus 6x plus 4. And then a little bit of simplifying by distributing the negative would help you see that the 4's will cancel out, and we'd just be left with negative 2x squared plus 6x. Now the little radius is the radius of the gap. So it's the distance from the axis of revolution down to the closer boundary for the region. So then we would do the y value of 4, because that's greater, minus the y values along this cosine curve, because those are shorter or less than 4. And that would give me my equation for these smaller radius values, which again was the radius of the gap on the inside. So when you're using washer method, what we're basically saying is that the area of each cross section, or the area of each washer, are these big circle areas, which is pi times big R squared, minus these smaller circle areas, which is pi times little r squared. The fact that we're subtracting out the small circles is what creates this gap in between them. We're just subtracting out that inner part. And then when we integrate that, so in this case we're going to integrate from 0 to 2 again, these points of intersection. When we integrate them, we're summing up all these washers. So we're adding up this one and this one and this one and this one. We're summing all of them up from 0 to 2, all these areas of these washers, so pi times big R squared, so all that squared, and then minus pi times the little r squared, and then integrating all of that. The integrating part is just summing it all up. And when you sum it all up, it creates the volume of this three-dimensional solid that was formed by rotating this region around the line y equals 4. Now you can pull the pi out of the integral if you want. So if you wanted to take this pi from here and put it out here, that is fine as well. And there would be our integral for the volume, the integral that would find the volume of this solid generated in part B. Now last but not least in part C, this is a volume by cross-section type of problem. So region R is forming the base of the solid. That means we're stacking the cross-sections on top of it and they're sticking straight up. Each cross-section is going to be perpendicular to the x-axis, so that's what tells us to do this with respect to x. And the cross-sections themselves are semicircles whose diameter is on the base. So they kind of run like this. You have this semicircle sticking straight up. This one would have a larger diameter. This one would get a smaller diameter. This would be small. And so just imagine all these circular cross-sections semicircular cross-sections all being stacked along this region where the diameter is perpendicular to the x-axis. So what I need to do is find the area of each semicircle. We find the area of each cross-section and then we integrate. The integration part is summing it up, right? This stands for an infinite sum. So we're summing up infinitely many of these semicircles all the way from 0 to 2 because we're stacking them this way so they accumulate as we move horizontally. So we go from 0 to 2 and we're going to just integrate that area formula. So that's what we need to find. The area of the semicircle in terms of x. So remember, this top curve was the equation 4 cosine pi over 4x. That tells me the height of each of those top curves. And then the bottom curve was the quadratic equation. So that's telling me all the y values from the x-axis to that bottom curve. So if I want to know the distance from the top part to the bottom part, I subtract these two equations. So I know the diameter of each of these semicircles is going to be the top function, the cosine 1, minus the quadratic function. So that's going to be my diameter. Now remember though, the radius of a circle is equal to half of the diameter. So I know that the radius of each of my semicircles is going to be half of the diameter. So then I know that the area of each semicircle, so these are semicircles, right, which is half of pi r squared because it's just the top half of a circle. It's not doing the bottom half of the circle. So it would be 1/2 pi times this radius squared. Now, to get the volume of this cross-section, I now just integrate from 0 to 2. That's summing up all the infinitely many semicircles between 0 and 2 that are sitting on top of this base. So I'm summing up all the areas of all these semicircle cross-sections. I can move the constant, which is pi over 2, out in front of the integral. And then I just have this radius squared inside my integral. And that would be the equation that represents the volume of this solid generated by these semicircular cross-sections. And that concludes this video. This was a long one. Thank you so much for sticking through. You guys are awesome. See you in class.